I know you guys are so pumped about this video. You have already heard all about the first fundamental theorem of calculus. Today, we are going to talk about the second fundamental theorem, okay? Real quick refresher. First FTC looked like this. The integral from a to b of f of x dx. That's so ugly. Oh dear. Let's fix that. F of x dx is equal to the antiderivative of b minus the antiderivative of a. Cool. Awesome. All right. Well, so let's think of area under the curve. Instead of just thinking of it as a value, let's think of it as a function. So notice here, I rewrote capital F of x is equal to the integral from a to x of f of t dt. What we're saying is that I know my initial value where I start my integral. I don't know what's happening. Like, I don't know where to stop because basically my area is going to accumulate. So here's the definite integral as a number. So when I plug in a to b, let's say I have my arbitrary function that I always like to go for here, okay, a to b, the area under the curve is all of this stuff right here, okay, maybe, oh wait, boom, right there. Oh, it's not changing color, that's sad. Let's try that again. Nope, it's just really not going to do it. Out there, whatever. All right, well, you know what, the effort was really there. All of this right here, okay, all of the area is the integral from a to b. So if I looked at the definite integral as a function, okay, looking at the same function, if I can draw it the same way, okay, I'm starting at a, but I don't actually know where I'm stopping. X could be here, and so I have this much area. Or x could be here and I have this much area. But either way, my function is growing, or I mean, it could, well, my function value depends on my x coordinate of my, well, of my upper bound, okay? So it's going to vary depending on where I stop. So I can plug in different values and my area is going to accumulate accordingly, okay? Let's look at an actual example so you can kind of see what I'm talking about here. So let's say I have the function f of x, capital F of x is equal to the integral from 0 to x of cosine of t dt. And I want to evaluate this at x equals 0, pi over 6, pi over 4, pi over 3, and pi over 2. Okay, so if we started out at just f of 0, so f of 0 is equal to the integral from 0 to 0 of cosine of t dt. Well, that's pretty straightforward. We know that any time that the bounds are the same, that's just going to be 0. Okay? So let's evaluate it at the next value. So f of pi over 6 is going to be the integral of 0 to pi over 6 of cosine of t dt. Okay? Well, I know that the antiderivative of cosine is sine, so sine of t from 0 to pi over 6. Okay? And then this becomes the sine of pi over 6 minus the sine of 0. The sine of pi over 6 is 1/2. The sine of 0 is just 0. So that function value is 1/2. So the area under the curve from 0 to pi over 6 is 1/2 of cosine. Okay, well, what about the other values? So pi over 4 would be the integral from 0 to pi over 4 cosine t dt. You guys are probably sensing a pattern here. 0 to pi over 4 sine of pi over 4 minus the sine of 0. And I end up with whatever the sine of pi over 4 is, so it's just root 2 over 2. Let's see, I've got f of pi over 2. So 0 to pi over 2 of cosine t dt is equal to the sine of t from 0 to pi over, did I skip a number? Oh, I skipped pi over 3. Oops, hang on. Make that a 3, make that a 3, and I hadn't written that yet, so 3, 3, 3. Okay, So the sine of pi over 3 minus the sine of 0. And the sine of pi over 3 is root 3 over 2. Okay, so then f of pi over 2 would be the integral from 0 to pi over 2 of cosine t dt, sine of t 0 to pi over 2 equals sine pi over 2 minus the sine of 0, which is, the sine of pi over 2 is just 1. Okay, so overall, is anyone sensing a general pattern here? Like if I were to say f of x here, from 0 to x, cosine of t dt, this is going to turn into the sine of t from 0 to x, which turns into the sine of x minus the sine of 0, which the sine of 0 is always 0. So this is just the sine of x. Interesting. So the function here of 0 to x, the integral from 0 to x cosine of t dt, that's essentially the same thing as the sine of x. So we'll go to the next page where I have a little bit more room here. And so since the area is now written as a function, we could take the derivative of that function. So remember, we had f of x was equal to 0 to x cosine of t dt, which we discovered that was the same thing as the sine of t. No, sorry, the sine of x. Once we're all said and done, sine of x by itself. Well, because I can write that as a function, well, that means I can just take the derivative of that function, and the derivative of sine of x is just cosine of x. Interesting. Okay, you're thinking like, well, what's the point of that? Well, okay, well, right now it's just taking the derivative. We can find lots of things. The rate of change, we can find the slope of the tangent line, we can do all kinds of things with the derivative, okay? But let's think about a non-trig function. So here, basically, the derivative of my integral got me back to basically where I started. That's odd. But you know what? It was a trig function. Maybe it was a fluke. So let's try this on a non-trig function. I want to take the derivative of this integral from 1 to x of 2t plus 1. Okay. So to work this, it's kind of, we don't really know what to do with the derivative and an integral yet. Like you guys haven't really learned that yet. So let's start from the inside and work our way out. We know how to integrate. So let's start with that. Let's start with integrate first. Okay, so I've got d dx of the antiderivative of this is going to be t squared plus t from 1 to x. Okay, that's not so bad. And so that's the integration step. Now I need to apply FTC and plug in those two things. So step 2, apply first FTC. So I'm going to have d dx of x squared plus x minus parentheses 1 squared plus 1. Okay, I can clean that up a little bit. That basically just becomes d dx of x squared plus x minus 2. Okay, and then my last step is to just differentiate. All right, so then I end up with 2x plus 1. Well, interesting. 2x plus 1 looks a whole lot like what I had before, but earlier I had 2t plus 1. So instead of a t, now I have an x. Well, that's curious. That's the same thing that happened on the trig function. Okay, well, let's keep going here. Surely that's a fluke. Maybe. Okay, let's make it a little bit trickier. So what if I had the integral from 1 to x squared of 2t? Let's see if that works out the exact same way. So the first thing we did a minute ago was integrate. So we're going to do that again. We're going to integrate. So we're going to have d dx of t squared plus t from 1 now to x squared. Okay, that's what's going to be different about it. All right, so then step 2 is apply first FTC. So I've got d dx of x squared squared plus x squared minus 1 squared plus 1. Now, some of us are like, wait. Why so many squares? Okay, let me help you out with some colors. Colors here. Nope. I want that. Too much. Okay. Nope. I will get this. Oh, that's what's wrong. Okay. Gotta go one at a time because those are somehow connected. Okay. So, and then let's make that one blue. Okay. Let's see. So, just like we plugged in our upper bound earlier into both terms, minus plugging in our lower bound, that's what I have done here, okay? It's just that now my upper bound is coincidentally also being squared. So there's my upper bound here, and again here, and then my lower bound here and here, okay? So, does everybody see what we did there? We just plugged in our upper bound into both of them, and then our lower bound. Okay. Let's see if we can simplify that out. dx. So that's going to be x to the 4th plus x squared minus 2. Okay. Then I want to differentiate from here. So then that's going to become 4x cubed plus 2x. That doesn't look quite like what I had before. But, is there anything I could factor out of? Yeah, I can factor this. I'm going to go ahead and factor out a 2x out of both terms. So take 2x out, and I'm left with 2x squared plus 1. Interesting. I'm trying to see if there's any kind. So earlier it was really easy to relate that we just basically, like in both the sine and the 2t plus 1, this upper bound essentially just got plugged into t here, okay? And that's what was left over. Well, we have something similar to that. So if I were to think of this right here as f of t, and this guy right here as g of t, okay, well this is f of g of t. Because if I were to think of f of x as 2t plus 1, plugging in an x squared would just turn into 2x squared plus 1. And then this guy right here, where's that 2x come from? Oh, well, g prime is 2x. Okay? So what's happening here is what we like to call the second fundamental theorem of calculus. Okay? So what's happening is when you have the derivative of an integral, okay? So the derivative of an integral from a to x of f of t dt, that's the same thing as just f of x, okay? You're plugging in the function into itself. I'm sorry, you're plugging in the upper bound into the function, and you're just left with f of t, okay? Because remember, we're thinking of area as a function itself, so we can take the derivative of that. Well, the derivative of that is, boom, just f of x. Okay, you're basically canceling out these two things cancel each other out is the goal here. Okay, but like we just saw on the last slide, what if we had a situation where it wasn't just x in the numerator, instead we have a function? Well, and if that's the case, you start out the same way. You start out as plugging in your function, this guy right here, into this function. So f of g of x, but then you multiply by the derivative of that upper bound, okay? So it kind of looks like the chain rule, but it's not the chain rule. Remember with the chain rule, you have that extra f prime of g, okay? This is just f of g of x, g prime of x. I know this seems a little bit tricky, so let's do several practice problems together and see if it'll help clear that up a little bit. Now, I'm using just the, I mean, we could do the whole long-winded process like we had been doing, where we integrate, then integrate first FTC and then differentiate and all that good stuff. But let's use the actual second FTC, okay? So in FTC, second FTC, d dx of integral from a to g of x of f of t dt is equal to f of g of x g prime of x. So I'm going to evaluate my function at my upper bound. So actually I have to take the derivative. So f prime of this is equal to my upper bound evaluated inside my function, x cubed, and then times the derivative of my upper bound, which is 3x squared. So this becomes 3x squared cosine of x cubed. Okay? Now, if you wanted to see this the long way, okay, if you wanted to see this the long way, just real quick, so d dx from pi over 2 to x cubed of cosine t dt. Okay, so integrate first, so d dx, the antiderivative of cosine is sine, so sine of t from pi over 2 to x cubed, okay? D dx of the sine of x cubed minus the sine of pi over 2, okay? So take the derivative. I have to use the chain rule on the derivative here, so the derivative of the inside is 3x squared times the derivative of the outside, so cosine of x cubed. Sine of pi over 2 is just 1, so the derivative of 1 is just 0. So I'm left with 3x squared cosine of x cubed, which is the same thing that I had up there. Okay, this is the long way to do it. Using second FTC helps you do this the short way. You are welcome to operate in this fashion. You are always welcome to do it the long way. We're just showing you the other way, so that way, because basically in math, every single time we come up with we see something repetitive, we come up with a pattern, test the pattern, make sure the pattern works, and then we just go with the pattern every time instead of doing it the long way. Just like finding integrals. We could take the limit definition of an integral every single time we wanted to. But oh my gosh, that's so long. Or we just use our antiderivative properties and go from there. And I'm going to be honest. Unless you tell me, I'm going to go with the antiderivative. Okay, let's do another one. Your favorite question. Does it get harder? Oh gosh, what happened? What happened here? So the top and the bottom, ooh, they're in a different place. Well, I know we don't really like that, but there's an integral property that we can use. I could rewrite this d dx as, and then times, or d dx of the negative of my integral of pi over 3 to x cubed. That's a little bit friendlier. We've seen that version before, okay? And so then we have d dx of negative, actually, well, this whole thing just becomes, the negative can be brought out front, so negative d dx of the integral of pi over 3 to x cubed cosine t dt. We did this one on the last page, so it's basically negative 3x squared times the cosine of x cubed. No? Yeah? Maybe? Perhaps? Maybe a little bit? Okay. So let's keep going. Let's practice some more. Ooh, here's a whole bunch of them we could practice at once. Okay. Ooh, but some of them are a little bit tricky. Okay, so cosine of t squared. All right. So this is going to be the cosine of x cubed squared times the derivative of my upper bound. Okay. And so this becomes 3x squared cosine x to the 6th. Okay? Like usual, I forgot to mention, if you want to try this out on your own and see how this goes, and then come back, that you're more than welcome to. Give it a try. Give it a whirl, a spin, a go, and then come back when you're ready. And make sure you get the same thing that we have. Okay? Let's see. Oh, this next one is a little bit different because I have an x and an x cubed on the top and the bottom. Okay, so just for this one, I'm going to do it the long way, and then again we're going to recognize a pattern to see if we can maybe do this the short way in the future. Okay, so d dx, the antiderivative of cosine is sine, so I've got sine of t from x to x cubed. Okay, so d dx of the sine of x cubed minus the sine of x. Take the derivative, so 3x squared cosine x cubed minus the derivative of sine is just the cosine of x. So the shortcut to this, okay, let's say I consider these as two separate little functions, so let's call that h of x and call that g of x, f of t dt. Now in this case, this is going to equal f of g of x, g prime of x, minus, oh, I knew I was going to run out of room. Hang on. Minus f of h of x, h prime of x. So we just subtract the top and the bottom, okay? So then if I were to try to do this one using my shortcut, I would say cosine of x cubed times g prime, so 3x squared, minus cosine of x times the derivative of x, which is just 1, but this still works out to be 3x squared cosine x cubed minus cosine x. So these end up being the exact same thing. Okay, this was the long version. This is using the shortcut where basically now if you have two bounds that are both non-constants, they're both functions in and of themselves, then you can just subtract them. Okay. Let's look at this. Okay, so let's do the shortcut practice on cosine of t squared. So then I'm going to have cosine of x cubed squared times 3x squared minus the cosine of x squared, because, you know, I'm taking care of this guy, times the derivative of x, which is just 1. So this becomes 3x squared cosine x to the 6th minus the cosine of x squared. Okay? I'm hoping this is starting to sink in a little bit. Here, I'm going to give you two more right here. Pause the video, try it on your own, and then come back. I'm just going to write the answers down for you real quick. Hopefully you already tried it and then came back. This is going to be, oh wait, f prime of x is going to be secant x tangent of x. And over here, f prime of x is going to be, so you're going to have x squared cubed times 2x minus negative x cubed times negative 1. So then you're going to have 2x to the 7th. Let's see, still negative x cubed. Okay. All right. Again, hope you paused it so you can come back to it. So yeah, I have several more examples that I'm going to throw up here. Basically, yeah, I'm going to let you guys try them on your own and then check the work in Canvas because this video is already pretty good, I think, gave you a pretty good idea. So yeah, that was the second fundamental theorem of calculus. Questions go to Prof. Rob Bob, Khan Academy, and your textbook.